So let's look at another conformal transformation. Now, in general, remember the flow in the z-plane, W2 of the z-plane, this is a complex velocity in the z-plane, can be written as a function of the complex velocity in the zeta plane divided by dz d zeta, where z is a function of zeta, or zeta is a function of z. There's some relationship between z and zeta. So let's start with flow in our zeta plane as just the flow over a circular cylinder, again with circulation. So we can write that as v infinity e to the minus I alpha plus I times gamma over 2 pi v infinity 1 over zeta. And we're just going to write it as for the cylinder located at the origin in the zeta plane. Then we've got minus r squared e to the I alpha times 1 over zeta squared. Okay, so that's just flow with circulation around a cylinder in the zeta plane centered at the origin. And now let's apply this, this transformation. We're going to say that z is equal to zeta plus r minus some constant epsilon squared over zeta. Okay, and we can rearrange this to get that, that zeta is equal to z plus or minus the square root of z squared minus 4 times r minus epsilon squared all over 2. Okay, and then we're going to need the derivative, dz d zeta. So let's take dz d zeta. And if we just take the derivative here, we get 1 minus r minus epsilon squared. That's just a constant divided by zeta squared. Okay. Okay, so now we're ready to plug all of this information into this equation here. So W2, our flow in the z-plane, is going to be equal to v infinity. Remember, we're plugging in W1 of zeta, where we're swapping out zeta for z. So it's going to be e to the minus I alpha plus I gamma over 2 pi v infinity. I'm going to leave it in zeta for a minute because it's just easier. So 1 over zeta minus r squared e to the I alpha over zeta squared. And then this whole thing divided by 1 minus r minus epsilon squared over zeta squared. Okay, so this is our complex velocity in the z-plane, where we can plug in this expression of zeta as a function of z. But let's first start by looking at, oh, excuse me, I forgot a bracket there. Let's look at what the geometry has done. So the surface of the circular cylinder in the zeta plane has now been transformed, and that surface was a streamline, right? So the surface of that geometry is a streamline. Let's look at how that streamline has changed as we've gone to the zeta plane instead. So if we look at, so let's look at the surface here. So we're going to say that the zeta surface was equal to r e to the I theta. So that's just the surface of the cylinder in the zeta plane. And we can use this transformation to find out what the z surface looks like. Well, it's going to be equal to, and what I'm doing here is I'm just plugging in this equation here, where I'm plugging in zeta surface here to solve for z surface. Okay, so the z surface is equal to a zeta surface plus r minus epsilon squared over zeta surface. And I can just plug in what that zeta surface is. So I'm going to get r e to the I theta plus r minus epsilon squared over r e to the I theta. Okay, so now I'm just going to rewrite this as r times cosine theta plus I sine theta plus r minus epsilon squared over r times cosine theta minus I sine theta. Okay, so the e to the I theta I've just split out into cosines and sines. And now I'm going to combine the cosine terms and the sine terms. And so what I'm going to get here is r plus r minus epsilon squared over r all times the cosine of theta plus r minus epsilon squared over r times the sine of theta. Okay, and this is z at the surface, so I can say this is going to be x plus iy on the surface. Okay, so so I can so this is actually now the equation for an ellipse. So what we've done here is taken this circle and used this transformation here from z to zeta, and we've come up with a surface here that looks like an ellipse. And so the flow in this z plane is now the flow over an ellipse with circulation. We left the gamut in there, from flow over a cylinder with circulation. So this is now flow over an ellipse with circulation. Okay, so let's look at there's a couple new things here. You might notice that in our original flow there was a singularity only at zeta equals 0. That was at the origin. Well, now that we've applied this transformation, we actually have two singularities, and those show up right here. If this term is equal to 1, then 1 minus 1 is 0, and that's in the denominator. And so this creates a singularity in the z-plane. And so let's look at what this singularity, what those singularities look like. So we're going to have a singularity or singularities at any time zeta is equal to plus or minus r minus epsilon. Okay, so because those are squared in the denominator there, because that's squared, it could be plus or minus. Okay, so that's our z singularity. Well, we can again use this transformation up here to find out. That was a zeta singularity. We can find out where those are in the z-plane, where those singularities actually map to. So our z singularities are going to be equal to our zeta singularities plus r minus epsilon squared over zeta singularity. Okay, so let's plug in our first one, where zeta s is equal to plus r minus epsilon. That's our first singularity. So that's going to give us a z singularity of r minus epsilon plus r minus epsilon squared over r minus epsilon. And so that gives us 2 times r minus epsilon. That's a positive. Okay, so now let's look at our other singularity. Zeta singularity is equal to minus r minus epsilon, and that gives us a z singularity equal to minus r minus epsilon plus r minus epsilon squared over minus r minus epsilon. And so that turns out to be minus 2 r minus epsilon. So our z singularities, zs are at plus or minus 2 times r minus epsilon. So that's where they are in the z-plane. Well, it turns out that these two singularities, let's just kind of draw out what this flow would look like. What we've done is taken in the zeta plane a flow over a circular cylinder, and we've mapped it to the z-plane. And it's now an ellipse, actually. So it looks something like this. And it turns out that those two singularities map to the foci of the ellipse. Let me try that again. The foci of the ellipse are those z singularities, and this is the surface up here. This is the equation for the surface of the ellipse in the z-plane. Okay, so what we've done here is applied a conformal transformation that now gives us flow over an ellipse. Now the original flow in the zeta plane was flow that could have some circulation. So the flow may have come in from one direction and left in another direction. And that's flow with circulation. And so here what we're going to find is that we can now map that to this flow over an ellipse with circulation. Okay, so we can get what that flow would look like over this ellipse with some circulation by using this conformal transformation. And this all came from just this general equation up here. This is just the general equation for a conformal transformation from one complex velocity in the zeta plane to a complex velocity in the z-plane. We just need this relationship between z and zeta, and this is the transformation that we applied here, and that produced flow over an ellipse.